Thank you very much, Gavin, for having both Dr. Shi and me. I am Ron Ramsaren, and I have been working at CTNav for over 3 years as a Director of Product Development in North America. Today, I'd give an overview of the global satellite system, constellations, signals, benefits, and some use case applications. The table shows the status of each satellite constellation characteristic parameters. Currently, there are 6 constellations, 4 global constellations: US GPS, Russia GLONASS, Europe Union Galileo, and China's Beidou, especially their MEO, medium orbit satellites, with 2 regional systems, the Indian NAVIC and the Japanese QZSS constellations. GNSS satellites orbit well above the Earth in the region space called medium Earth orbit, which is located above low Earth orbit and below geosynchronous orbit. The medium Earth orbit is ideal for satellite navigation and communication satellites. From the table, GPS and GLONASS satellite orbits at altitude close to 20,000 kilometers or 12,000 miles. Galileo and Beidou, medium Earth orbit satellites, orbit around 21 to 23,000 kilometers or 13 to 14,300 miles. The NAVIC and the Indian constellations, NAVIC, Indian constellation, and the Japanese constellation QZSS, are regional constellations in the geosynchronous orbit, which is really greater than 35,000 kilometers. The table also shows the number of satellites within a constellation along the current number of satellites that are operational. So as you can see, for instance, GPS has 32 total satellites, but currently there's 31 operational, and Beidou 35, they're aiming for with 21 operational, and Galileo is about 15 satellites operational. So the figure shows all of the constellations. The yellow dot on the top left corner, there's a yellow dot among the satellites, is where I'm located in Calgary. And seeing with the COVID-19, everybody's at home. So I took our GNSS I-90 receiver and I stuck it out between our homes. And roughly at that time of the day, I can average anywhere around 22 satellites in open skies, considering I'm among houses, trees, and what have you. The GNSS satellites transmit signals comprised of carrier frequencies, a range code, and navigation data. A single satellite typically transmits several signals shown in the table. For instance, GPS has L1CA, L2C, and L5, whereas Beidou has B1A, B2C, and B3. GNSS frequencies are commonly referred to as bands. All the GNSS frequencies fit into either an L1, L2, L5, or L6 band, as defined by the International Telecommunication Union. International cooperation was needed in the development of these frequencies, since each constellation signal were designed close together so that a single GNSS receiver, just as some of the ones you've seen in previous slides, can receive multi-constellation signals without interference between signals. For example, L1 band consists of a GPS L1CA, GLONASS L1 or G1 as it's known, Galileo E1, and Beidou B1, even though their center frequencies are close but different, and no interference within your GNSS receiver. A combination of signals from each constellation, for example, the lower band ranges between 1151 to 1214 megahertz. Provide services suitable for safety of life applications because there's no interference on these bands, particularly with the GPS L5 and the Galileo E5. The other frequencies provide standard positioning services, or SPS, precise positioning services, open service, for instance, Beidou and Galileo, and high accuracy service, which is utilized by multi-constellation GNSS receivers, such as CCI-90, which you would see some data in really robust environment conditions. A combination of multi-constellation observations can offer improved reliability, availability, and accuracy for position solutions. So for instance, satellite blockage, its benefit with multi-constellation receivers, whereas if you have one constellation being shadowed at that particular time, you have the other three constellations you can depend on. Improved illusion of precision for better distribution of satellites in view. Improved robustness in spoofing detection. More efficient receiver autonomous integrity monitoring, known as RIM, for your fault detections on your signals. Faster signal acquisition time, and better accuracy in position and time. 5 benefits to users with the multi-frequency receiver: improves accuracy by better estimates and compensate for ionospheric delays, which is really the biggest error in GPS or GNSS. Precise range measurements, improve in ambiguity resolutions for RTK and precise point positioning techniques, which Dr. Xu would go into in a little more detail. Immunity from interference on a frequency allows the receiver to function with other frequencies. So for instance, if you were in interference with GPS, you would have Galileo, Beidou, or GLONASS on your receiver that would allow you to still maintain a certain level of accuracy. Wideband signals improve noise multipath mitigation techniques. The next few slides shows the PDUP, the precision, delusion of precision performance for the 4 global constellations. The more signals a GNSS receiver can see spread apart, the better precision the receiver's position becomes. So for instance, at 5 a.m. on July 20th, 2020 shows the following poor PDUP performance. GPS over parts of Africa and Kazakhstan and Russia. GLONASS over Cambodia, Taiwan, and the Pacific Ocean. Glad I remembered my geography. Next slide, please.
Yes.
Galileo. So as you can see, Galileo overall poor performance. Since there are only 15 operational satellites right now. Beidou, better coverage over Africa, Asia, and Russia. As you can see, by using a multi-constellation receiver, we gave a better accuracy solution for the time versus a single constellation receiver. So if we had a multi-satellite receiver, say for instance, where the Galileo PDUPs are weak, you would improve your satellite geometry. In the next few slides, an I-90 receiver was placed up against a wall, which only allowed for half-sky view of the satellites. The result shows the multi-constellation receiver performs better in these challenges. Now, we actually ran these tests. I mean, it's probably not normally used out in the survey field, but it's just to show you the real diverse effect of multi using multi-constellations versus a single. As you can see, on just a GPS, with GPS turned on, your horizontal accuracy is between 1.1 meter to, with GLONASS, as you can also see, in this case, it did not really help very much. But with the four constellations, GPS, GLONASS, and Beidou, you're able to see where the accuracy becomes 0.19 meters. Again, I got to apologize for my units. So 0.19, probably about a foot. Again, the slides were made both in Canada and... So this other slide shows the actual raw data from the GPS only. As you can see, GPS has a period of float solutions between 1830 and 1845 with some biasing because of probably poor satellite geometry and not being able to track the full constellations of all satellites. Next slide, please. GPS and GLONASS shows similar results within that same time period. So again, you could probably assume that those satellites were either being blocked from that portion of the sky. Shows a well-proportional, your signals are really coming through really well. Shows improvement with a small window of float solutions with reduced biasing. Here we go again in an extreme condition under really thick foliage out in Shanghai. The I-90 receiver was placed under such conditions where open sky view is highly impossible. The results shows a multi-constellation receiver performs better in these challenging areas. So for instance, again, as you can see here, under the horizontal accuracy with GPS, we were seeing somewhere around 34 meters, whereas in GPS and GLONASS, we actually saw some improvements. You can see it drop down to 23.5 meters. And then with the full constellation, again, we are down to between a foot or 0.1 meter. Again, if you look at the data from this slide, GPS only, more areas of autonomous and float solutions. So again, just having one satellite constellation being GPS within this area would give you those types of readings from your receiver. With the GPS and the GLONASS, you can see where shows some improvement with more available signals. So therefore, we got just a little pocket of float and autonomous solutions between 1930. And as you can see, under those tough conditions, again, although you're under thick foliage, you can see some amazing improvements. You were still able to receive probably signals from all of the constellations. So again, there's hardly any, well, there's no autonomous solutions, just a few float solutions as shown. So just to recap, so the I-90 receiver is the receiver shown in the picture that was actually used. It's a smart receiver, it's a smart GNSS receiver integrated with CHC NAV IMU RTK technology to provide a robust and accurate GNSS position in any challenging environment shown in any of the previous slides. The I-90 combined a state-of-the-art RTK engine, high-end calibration free IMU, and advanced GNSS tracking capabilities to dramatically increase your RTK availability and reliability. The I-90 Smart Receiver performs well in geodetic applications, accurate stakeout for pipelines and cables under thick foliage as shown in our worst case scenario. As-built and stakeout applications in construction, mining, and real property surveys are where our clients sees the best improvement and in performance of a multi-constellation receiver. The P2 Elite is another multi-constellation GNSS sensor. It's a dual antenna, high precision IP67 receiver with embedded 4G, Bluetooth, Wi-Fi, and UHF radio modem, designed to provide reliability and precise head-in and position solutions for demanding applications such as machine controls and marine applications where equipment is close to each other or side by side other equipment, or steep slope faces, which create signal blockage and multipath in particularly mining and construction survey applications. As you can see, multi-constellation product usually uses these GNSS receivers for surveying applications, precise agriculture for guidance and machine control, surface leveling, planting, and seeding. Construction, again, in machine control for hydraulics, automatic hydraulic movements where you need an accurate solution, especially to control your blade accurately. In marine applications, again, construction, marine applications, and safety of life at sea. Also, we find that some of our clients have been using our products within the course networks for multi-constellations in order to provide their clients the RTK solutions that contains all of these frequencies and satellite signals. I'm providing some links for extra reading, just on some references based on the different constellations. And that's the end of really my presentation. And now I'd like to introduce my colleague, Dr. Shi, that would present the L-band PPP applications. Thank you.
Thank you, Ron. Hello, everyone, and thank you very much for giving me this opportunity to share some of my ideas about PPP applications. I've been working on PPP for 16 years, basically deriving algorithms and writing softwares. So today I would like to start with a quick review of GNSS positioning technologies, and then I will move on to the L-band PPP survey structure, and I will focus on the reference stations network and external universal L-band modem and give you a little bit more details. After that, I would like to show you some PPP corrections accuracy and PPP positioning results. And in the end, I would love to talk about the typical and emerging L-band PPP applications. So the GNSS positioning technologies. If we start from the left-hand side top, and it's a standalone calculation. This is the original, very basic calculation. It is based on pseudo-range. The idea is if I know where the satellites are and I can observe my distance from the satellites, and I can calculate my receiver's 3D coordinates and the time. So we call that pseudo-range based. It's because it is not the real range. It is distorted by the GNSS errors. These errors can be related to satellites or the signal path or the receiver itself. So the idea is to remove these errors that we can have better accuracy, because standalone accuracy for GPS only is just 10 meters. So there are two approaches to eliminate or reduce the GNSS errors. One is called SSR, another one is called OSR. So the SSR is state space representation. Basically, it means we model what these errors are, identify them, and work out the values, and we send these values to the user. Another approach is OSR, is observation state representation. So that idea is, well, what if I don't bother to work out what the errors are? I just send the observations from another known position reference station not far from the user. And then the user will be able to use the observations to do a relative positioning. And that is called DGPS. And DGPS can successfully improve the accuracy from 10 meters to meter level. And then people started to use carrier phase in addition to pseudo range. And that carrier phase is more accurate observation of the distance between the satellite and the receiver. However, by using carrier phase, you're introducing in a new error, which is called, or a new unknown, which is called a carrier phase ambiguity. So the RTK is basically sending you the carrier phase observations as well, so you can cancel out the carrier phase ambiguity. So you can work out the carrier phase ambiguity by fixing them to integer numbers. And if you build more reference stations, you will have a network RTK service. So if we come back to the left-hand side about SSR services, and if we send the GNSS errors, for example, the major ones are the satellite orbit and clock by the geostationary satellite, and we will have a SBUS service. Examples will be IGNOS and WAS, but these are regional or local coverage. So if we want a global coverage, and if we want to have very high precision, let's say the carrier phase, using carrier phase to achieve centimeter or decimeter level accuracy, we can do PPP or PPP-AR, or in the end, PPP-RTK. I will talk about the differences of these PPP, PPP-AR, and the PPP-RTK services later in my presentation. Okay, here is the PPP service structure. So we use a global reference network. We don't need too many stations, like 70 to 100 stations, to observe the GNSS satellites. And then we work out the precise orbit and clock in real time. And we form SSR corrections and uplink these corrections to geostationary satellites. And these corrections will be reflected to the Earth, and the users will be able to receive them. So if the users have the modem to receive L-band corrections integrated within the device, then they can directly do the calculation. But if they don't, they will need some external modem, as shown here as L-band modem. This modem would be able to convert SSR to OSR. So some more details about this reference network. I have put an example of a network of CHC in a Chinese province of Hainan province. This is basically a tropical island. And we have covered this island with 21 stations. A typical distance between two nearest stations is 40 to 50 kilometers. This is much higher density than the PPP calculation. We have done this, but a much lower density than RTK. So we have done this to actually achieve PPP RTK service. So if we want to cover the whole China, and it's quite hard to see, but there are 1,817 stations here. We have finished 1,047 stations, so 770 to go. I'm putting this picture here to show that we actually have built more stations in the places where the economy and the population is higher, which means we have more users. So for more users places, we build more stations to enhance the service position, the service performance there. And then is the external universal L-band modem. So for existing receivers who do not have these L-band modems integrated inside, then we have made a product. This thing can receive L-band SSR and convert SSR corrections to OSR corrections using VRS, virtual reference station algorithms. Then it can broadcast up to 10 Hz OSR out via Wi-Fi. And we have also reserved 4G and Bluetooth capabilities in it. So some results. And as I said just now, the main GNSS errors are the satellite orbit and the clock. And if we look at our accuracies in determining the satellite orbits and clock, here we have just a couple of centimeters error for GPS, GLONASS, and Galileo system. Our Beidou orbit is a little bit less accurate than the other constellations, mainly because of the reference stations coverage. And the clock are almost the same. And here is the results of PPP, PPP-AR, and RTK solutions. I've been using these solutions to process the same period of data and put these three lines of results overlapped in one plot on the left-hand side. The red one is normal PPP, and the yellow one is for PPP-AR, and the green one is for PPP-RTK. As we said, to use carrier phase to achieve centimeter level accuracy, the carrier phase ambiguity is a problem. So for PPP, we are not resolving any of these ambiguities. We just keep them float. But as we're using a common filter to work over time, then when the common filter has achieved convergence, then we can also get very good results. But it will take a period of time to converge first. So you could see in the beginning time, it took like 10 to 20 minutes to converge. But the PPP-AR, we are sending some extra information to the receivers in addition to the clock and orbit, which is ionosphere information. Then during the PPP is trying to converge, there will be a point that the solution is good enough, or let's say the residuals are small enough, and then we can resolve the ambiguities to integers. So that is called PPP-AR. Then you can see the yellow line would just suddenly drop to a very low level. And for PPP-RTK, we send even more corrections to the receivers. So the residuals are even smaller, and then we can directly resolve ambiguities from the very start. And the results are on the right-hand side. So for PPP, we're not trying to fix any ambiguities, so the fixed rate is 0. And for horizontal and 3D accuracies is 5 centimeters and 1 decimeter. For AR, we have almost a very similar accuracy, but the fixed rate is 95%. And for PPP-RTK, we have improved the accuracy, and the fixed rate is 99.9%. Here is one slide for the applications of PPP, very typical applications. So as we discussed before, one priority or one advantage of PPP is it doesn't need a reference station network to be next to the user. So the main application area has been marine for offshore drilling, seismic, diving, surveys, subsea constructions, because there is no place to put a reference station. And on land, actually, the agriculture has been a rising market. And here I have provided a picture of our agriculture product, L-band PPP enabled positioning. We have put the receiver and IMU within the steering wheel. So you need to do, so the change of a normal truck is very easy. You just take off the original wheel and put this on. Then you will have your PPP solution enabled. And the farmers can just switch on the device and go to have a cup of coffee. And when they come back, the solution has converged, and then they can start to drive. around. And also putting the IMU in there actually help a lot, because PPP will face lots of difficulties when the truck is turning around. Then having the IMU is a very good augmentation of GNSS itself. Emerging L-band PPP applications. I have just selected drone as one topic. People might say automotive or IoT, but I'm particularly interested in drone. You can see our current market of drones include the topographic survey, construction, asset inspections, mining, natural resources, etc. These are all suburban. So can we really fly a drone in the city area? This will actually face lots of difficulties, especially the privacy and the security concerns, that you need to create bubbles in the cities that you do not allow the drone to enter. To achieve this, the drones must be very accurately positioned, and they should have an automatic program to just land it if it has entered the bubble. So currently, for most of the drones, they are controlled by ground radio transmitters, and the drones can't actually fly too far away from the controller. There are actually 4G mobile network controlled drones, but receiving L-band signals from the drone is very difficult, because the signals actually come down from the geostationary satellites that are above the equator. So you need to actually point your antenna to the geostationary satellites. If you are flying a drone and the drone is just speeding up or just turn around, then you will lose your L-band signal stream. So receiving L-band can be really difficult. And then we have come to a point, just think about, is PPP just mean L-band? Can we use any other communication channels? For example, 4G or LEO or anything else, or LT? Then PPP can be greatly improved, especially in the areas that it can be used. But to do this, we need to change the format or the method that we use to send PPP corrections. When we use L-band, we are creating a communication stream. But if we are sending via internet, for example, we need to change the streams to packages. And then the user might miss some packages, but once they received enough, they will be able to do the positioning. So the new formats and new contents and new algorithms are needed. Okay, thank you. And thank you very much. And any questions, please?
Thank you, Ron. Thank you, Dr. Shirt. Yeah, a couple of questions. Gary B asks, have you done performance comparisons between different bands to see which combinations do better? Example, L1 plus L2 versus L1 plus L5. And one that I'm struggling with right now, do I choose B1, B2 or B1, B3? So,
Ron, do you like to talk about it?
Would you like to take it? Or actually, what we're hearing from our customers, really the band B3, a lot of customers are really interested in using those B3 bands within North America. Currently, I haven't personally done any testing with those bands, but I see that a lot of our clientele are requesting us to open up all of the constellations and signals within our receivers to do those.
okay, Dr. Chur, the L1, L2 been around for a long time, and the L1, L5, with L5 being a more modernized signal, would you expect it to be better than L1, L2?
Yes, actually, for the ambiguity resolutions, if you have two frequencies closer, then they will form a wider lane, then it's easier for you to actually resolve. So that is one concern. For example, the E5, Galileo's E5A and E5B. Another thing is the signal strength and also the signal's other characteristics. For example, if we have some combinations that can be more resistant to multipass, there have been lots of research in these areas, and we have been trying to form all kinds of different combinations and compare the results. So the basic idea is to try to use all of them. So.
Okay, that's even better. Well, that's a lot of horsepower needed. And correct me if I'm wrong, but when you're working with multiple satellites, multiple constellations, and multiple signals, you need at least two of any constellation to put into a solution because one has to resolve the clock. Or I've heard this.
Right. The dual constellations, the dual frequencies calculation is mainly for the ionosphere remove.
Oh,
Right. So the ionosphere has a ratio connection with the frequency itself. So if you combine the frequencies with in a certain way, that you can actually cancel out the ionosphere, which is a big GNSS error.
okay. A question from the audience. Do you plan to build reference station network outside of China for PPP RTK services?
And that's a good question. we are planning to do that. Yes. Yes, we do plan to do that, but I'm not aware of the exact time schedules or anything. But we do have this plan. Yeah.
Okay. Okay. A question about the PPP RTK. So it's understood that, yeah, you're unless you add the ionosphere, you're not going to fix any ambiguities. You know, it's never really going to fix. And it's always sort of been, I don't know, the conventional wisdom for those of us outside of your algorithm community, that the reason why the vertical on PPP was not so good was because it couldn't refine down with things like the tropospheric, which is a local. So is your PPP RTK providing, for instance, a little bit of tropospheric data?
Yes, the troposphere is estimated together with in PPP, the troposphere is estimated together with the coordinates and the receiver clock. So if you estimate that, it means it takes longer time to actually converge to a certain point. And you are not really sure that if it has been completely decorrelated from the coordinate, which means I've got some error. Have I put it in the wrong place? Is it in the position, or is it in the troposphere, or actually it is in the receiver clock? We do have methods to do so, but it is not as good as the resolved ambiguities, let's say.
Oh, okay.
Right. So if you have resolved the ambiguity, we know for sure that what error is. And to resolve PPP RTK, we need to send people the corrections of troposphere and ionosphere together.
Okay, and got time just for a real quick question here at the end. Oh, now I can't remember what it was. Somebody asked me to ask you. Oh, your advantages of multi-constellation. You listed I had like 10 different advantages. I didn't see multipath listed. It would make sense that with the more signals you have, the more chance you have of catching the outliers. Is there a gain for multipath mitigation in multi-constellation?
Ron?
Dr. Shi, do you want to take that? Yeah, I believe we did talk a little bit about multipath on there. But yes, within some of our algorithms, we do have multipath mitigations within our product lines.
Okay, now the gains in the RAIM, the receiver autonomous integrity monitoring or measurement, is the gains in that also helping you estimate what your resolved positions are? or is that a separate set of data?
That is, I guess that's a separate set of data we actually optimizing from our module manufacturer
Okay.
right now. Yeah.
RAM is basically providing you the extent that you can believe that you are having a correct result. So it's like a when we say integrity, it's just basically saying to what extent you can trust the positioning results.
Okay. And when the user with the receiver is looking and they see the estimated positioning, say with RTK, that's typically displayed as a 1 sigma. Is that correct?
Yes. 1 sigma is mostly our receivers unless we state it's a three-dimensional 3D positioning, 2 sigma, 95%.
Oh, okay. Well, gentlemen, thank you for taking the time, and Dr. Sher, sorry about it's late night for you in the UK.
No, it's
And
okay.
Ron,
It's alive and well.
you're only an hour away in Canada, so I hope this didn't mess you up too bad. So,
No, it's just cold here.
oh yeah, you're going through a frosty freeze up there right now, going from
Exactly, yeah.
90 degrees to freezing
To
overnight.
about 60 degrees right now.
Oh, good Lord. Gentlemen, thank you
So-
very much. With this, we're going to wrap up the final session of today.